The fundamental theorem of algebra. Now, I have to warn you, your book's version will be slightly different. I kind of combined two theorems to make the fundamental theorem just to simplify things. That's what we're talking about today, the fundamental theorem of algebra. The goal is to find the zeros of a polynomial, pretty much the same goal as in the last section. So what does the fundamental theorem of algebra say? It says that any polynomial with degree n, now n is going to be a counting number, right? Like 1, 2, 3, 4, blah, blah, blah. With complex coefficients has exactly n zeros, as long as you count multiplicities. So very easy to understand, and people knew about this for probably hundreds of years, but it wasn't until Gauss proved it that there actually existed some rigorous way of showing it's true. He proved it when he was like 19. His proof wasn't quite perfect, but for a 19-year-old, it was pretty good. Anyway, you don't have to worry about proving it. We're just going to use the theorem. Okay, so we're going to find the zeros of p of x equals x to the fourth minus 3x squared minus 4. So my suggestion is to first list the possible rational zeros. It gives you a starting place. So to list the possible rational zeros, we find the factors of two things. What are they? We want to find the factors of what two numbers?
The first and the last.
Yeah, actually, I do the last first.
The last and the first, sorry.
Because it's the factors of -4, the constant term that'll be on top when you form the possible rational zeros. So I like to do that one first. So what are the factors of -4? And you include the plus or minus on the outside, curly bracket. What are the factors of -4?
1, 2, 4.
1, 2, and 4. Plus or minus on all of them, right? And then the factors of what else? 1. Oh, that's not very interesting. Plus or minus 1. So actually, the factors of -4 are your PRZs, right? Your possible rational zeros in this case, because the lead coefficient was 1. So once you notice that, you don't need to show this much work, at least when your leading coefficient is 1. So there's your possible rational zeros. Now, at this point, if you don't have a graphing calculator, you could just try. There's only 6 of them, right? You could try them using synthetic division to see which ones work, and it wouldn't take that long. But the calculator does make life easier, so let's use it. And then I'm going to graph it on a standard screen, at least for now. If you need to make adjustments, you can. Okay, there we go. So, okay, according to the fundamental theorem, how many zeros do you expect to have? 4, perhaps including multiplicities. How many real zeros do you see based on the fact that they correspond with the first coordinates of the x-intercept? Looks like only 2, even if you include multiplicities, because it looks like it passes right through, in both cases, in both intercepts, it looks like it passes right through the x-axis, straight through. There's not even a bend in it. When there's a bend in the curve, you might suspect that the associated factor with the x-intercept, the x-coordinate of the x-intercept, the 0, in other words, if there's a bend in the curve, you might suspect that the associated exponent is like 3 maybe, or 5, or some odd number. But when it goes straight through, you expect the multiplicity on the 0 to be 1. So it sure looks like there are just 2 zeros, real zeros. But that doesn't tell us about complex zeros, does it? Okay, so which 2 does it appear that they are out of our list of prime suspects from the PRZs?
Positive and -2.
Sure looks like positive and -2. Let's verify. So how do we verify? Good old synthetic division. What am I going to put up in the corner? Okay, start with 2. That's fine. And then across the top? 1, 0, -3. 0. Do you guys see where the zeros come from? Yeah, placeholders for the x cubed term and the x term. Okay, bring down the 1. What goes here? 2. What goes here? 2. What goes here? 4 here. 1 here. 2. 2. 4. As expected, we get 0. And the beautiful thing about this is we're pretty darn positive it's going to be 0 for the remainder. So you just got to find your mistake if you don't get it, right? And you could even check on the calculator, plug in 0. And when you hit the trace button on the calculator, plug in 0, make sure the y value is 0. Okay, so on the remaining quotient, the coefficients of the remaining quotient, we're going to perform synthetic division again. What do we put up in the corner? We want to verify -2 is a 0. Okay, bring down the 1. What goes here? -2 times 1 is -2. What goes here?
0.
0.
0. 1. -2.
And of course, 0. So this wasn't just an exercise. Your calculator is not going to help you find the remaining zeros. But the quotient that remains will contain them. So you had to do the synthetic division anyway. It's not just to verify that plus and minus 2 are zeros. You had to do the synthetic division to get the remaining quotient down to a quadratic. That's the key, because we have the quadratic formula if necessary. So what quadratic do these remaining coefficients correspond to? So the remaining quotient is x squared plus 1. And to find the zeros that x squared plus 1 contains, the remaining zeros that the original p of x contains, in other words, what do we do with x squared plus 1?
Solve for x.
Set it equal to 0, yeah, to find the remaining zeros. And we don't need to use the quadratic formula here. This is another one we can solve just by solving for x squared first, right? X squared equals -1, so what does x equal? Plus or minus I, right? So you take the square root of both sides, you get plus or minus square root of -1, which by definition is plus or minus I. So can you list the zeros for me?
Plus or minus 2, plus or minus I.
So how many are there altogether? 4, which is exactly what we expected from the fundamental theorem. 4 zeros. Okay? Make sense? Now, I, plus or minus I, don't correspond to anything on the xy plane when you graph it, which is why it didn't show up in the graph. So your calculator only goes so far. It's only so useful. It helps you find real zeros of a polynomial. It doesn't say anything. It doesn't help you as much with irrational zeros, that is. And it certainly doesn't help you at all with complex, although you can do some things with complex numbers on your calculator.